This chapter's focus is traditional telephony. In the last two modules, we looked closely at analog telephony, which has been relatively unchanged for decades. Now, we'll look more at modern digital telephony technologies. It would probably be accurate to describe SIP and other VoIP protocols as digital telephony, but when we use the term here, we're specifically referring to traditional circuit-based technologies that were widely adopted after analog telephony but before voice-over IP technologies. When we finish this discussion of fundamental concepts of digital telephony, we'll demonstrate how to configure the DoTi interface cards that can connect a digital trunk to Asterisk. The earliest digital telephony technologies are now almost 50 years old. In the decades since they were first introduced, the basic related technologies have been refined and improved immensely. Today, digital telephony standards and protocols have completely replaced analog telephony in many applications. While the hardware for digital telephony is often more expensive than analog hardware, the benefits in port density, audio fidelity, and reliability often justify the expense. In environments where there are a large number of ports, digital equipment is often less expensive than analog equipment on a per-port basis. Analog lines suffer from the limitation of only being able to carry a single call at a time. If a given line is in use, no other calls can be carried on it. Modern analog telephony offers features such as call waiting and three-way calling, but these don't eliminate the limitation. There's just no way to carry more than one simultaneous bidirectional audio conversation on an analog circuit. However, encoding audio and signaling data into ones and zeros allows a circuit to concurrently carry a much greater quantity of information. This is the foundation of digital telephony. With the efficiency gained by digitizing telephone communications, two twisted pairs or a single fiber connection can carry many simultaneous calls. This makes it much easier and cheaper to allow more than one concurrent call from the same premise. In the past, a separate twisted pair would have been necessary for each concurrent call. In North America, these digital circuits are known as T1s. A very similar connection known as an E1 is common in Europe and most other parts of the world. We said in the last slide that T1 and E1 connections gain efficiency by packing multiple calls onto a single trunk line, but we didn't describe how this is possible. Digital telephony uses a concept called time division multiplexing to achieve this. Multiple distinct digital streams are multiplexed into a single stream by packing just a fraction of a second of data from the stream of each of the channels into a transmission frame in its own time slot. A frame is transmitted after it's constructed, and the next slice of data from each stream is put into a new frame. This happens very rapidly. 8,000 frames are constructed and transmitted each second. The frame size and transmission rate are constant. Demultiplexing, or extracting the data from each time slot by unpacking the frame, occurs at the remote end of the link. The basic model is similar to a situation where multiple freight trains are destined for the same distant location. Instead of having multiple lines of track between the current location and the ultimate destination, the cargo from each train can be loaded onto a single train for transport. That one train uses the track to get to the destination, and then the cargo is unloaded when it arrives. For time division multiplexing to work, frames must be constructed in a very specific arrangement. The arrangement and synchronization of these frames is referred to as framing. There are multiple framing specifications defined. On T1s, DoTi supports D4 or superframe and ESF or extended superframe. The E1 standards of CAS or channel associated signaling and CSS or common channel signaling are also supported by DoTi. The framing method used on a given digital trunk will depend on how the line in question is provisioned. Usually D4 for T1 and CAS for E1 are used for older circuits, and ESF or CCS are used on more modern circuits. If your T1 or E1 is being provisioned by a telco, they will give you the provisioning details necessary to establish the connection. T1 frames consist of 24 time slots or channels and have a total bandwidth of 1.544 megabits. E1 frames use 32 time slots and have a total bandwidth of 2.048 megabits. The inner workings of T1 and E1 framing aren't relevant to the everyday administration of an Astra system, So we won't go into further depth here. There are numerous resources available on the internet to describe each framing scheme in detail. Framing dictates the organization of the data, meaning where one frame ends, the next frame begins, which time slots go where, and similar details. Framing is overhead that packages the data properly. There's another concept called line coding that is important to digital telephony. Coding dictates how the data itself is represented inside a frame. It's necessary to encode the data on a digital line because of the underlying electrical nature of the link. Zeros and ones are communicated by varying voltage on the line. These variations help the two endpoints of the line remain synchronized. But too many zeros or ones in a row can cause a loss of synchronization if there is no voltage variation to clock from. Loss of synchronization on a digital line would be devastating because the precise ordering and packing of frames would become meaningless. With no synchronization, an endpoint would be unable to tell where one frame ended and the next began, so it couldn't properly unpack the frame contents. Fortunately, most of the common coding schemes are designed to prevent synchronization loss and to recover from it if it happens. Dottie supports 3 of the most common coding schemes. AMI, or alternate mark inversion, is the predecessor of both of the variants widely used. B8ZS is generally used on T1s, while HDB3 is generally used on E1s. In their most basic form, T1 and E1 links are simply binary data carriers. They may carry channelized voice, but they could also carry something like a TCP/IP data stream or some other digital service. In fact, one of the most common digital services carried on a T1 or E1 is ISDN, specifically PRI. ISDN, or Integrated Services Digital Network, is an ITU standard that specifies robust digital telephony services. PRI, or Primary Rate Interface, is one implementation of ISDN that uses T1 or E1 as a carrier and typically trunks between switches. ISDN also specifies BRI, or Basic Rate Interface, for smaller connections geared more toward powerful features on digital phones. Dottie and Asterisk support both types of ISDN, and Digium offers Dottie interface cards for each. PRI allows for call control and other services to be handled by out-of-band signaling instead of in-band audio. This is done by separating the available time slots into one data, or D channel, and leaving the remaining channels as bearer, or B channels, for voice calls. The data channel is not used for voice traffic, and is instead used for out-of-band call control and signaling. This provides for more intelligence and a deeper level of control over call setup and teardown, as well as progress notification and call data like caller ID and dialed number identification. The capacity of a PRI connection is one channel less than it would be for a channelized non-ISDN configuration, but the trade-off is almost always worthwhile given the increased reliability in call control. T1s typically use the 24th time slot as the data channel, while E1s use the 16th time slot as the data channel. We introduced the basics of digital telephony in this module. We discussed the advantages digital telephony has over analog telephony and looked in detail at how digital communications work. We covered time division multiplexing, framing, and coding. Then we talked about ISDN, including both PRI and BRI. Next, we'll look at the Dottie interface cards that connect digital lines to Asterisk and how to configure them properly.